Hi guys, so today we'll be talking about the derivative. Now, the derivative is one of my favorite concepts in mathematics because it's very relevant to my field of study. But what is the derivative? Well, today we'll be talking about the very basic idea of the derivative and why it's important. Before we start, I want to just mention some applications of the derivative and why it's so important in the real world. The derivative has a lot of applications, not just in science and engineering, but also outside of it. In science and engineering, the derivative is a very, 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 very important concept. So if you're going into fields like physics and engineering, you will see the derivative. You can't avoid it. So you really got to get comfortable with the derivative. Outside of science, if you're really not into STEM applications, you'll see the derivative in business, economics, and social sciences. So basically, the derivative is in a lot of places. It's relevant to many fields because of what it brings to the table and what it means. The concept is very relevant. So, what is the derivative? That is the question. So, let's get started. Well, the derivative is a special type of limit. Now, that statement tells us a lot, and at the same time, it's kind of vague. It doesn't tell us a lot. Well, let's get a better sense of the derivative. You can think of the derivative as giving us the instantaneous rate of change at a point on the function. So the instantaneous rate of change is basically the rate of change at some point on the function. At some specific point, you can find how fast the function is changing. This can also be interpreted as the slope of the tangent line at that point. So if I were to draw a tangent line to some point on a function, the derivative would give me the slope of that line. So essentially, the derivative in itself can be thought of as a function that when you input a point, it will give you the slope of the tangent line at that point on a function. So that's a lot to take in, but let's discuss this a little more deeply. And we're going to go back to what I just said just recently. The derivative is a special type of limit. Now, I'm gonna go off this slide thing because I need the pen. So going back to what I said before, that the derivative is a special type of limit, I want you to consider this diagram I've made. Now, consider 2 points. Consider the points. Consider the points P, which is at A, F of A, and Q, which is at where X is not equal to A. Now, these points lie on some curve C. Okay, so we got this diagram, and I'm going to explain this diagram. So, let's start here, where you see the letter Q, right here. Just scribbled on it. We got our point P right here. Now, let's consider the secant line. So, the line from P to Q. So if I were to draw a line straight from P to Q, and you can see it right here in black, consider that line. So how do we find the slope of this line? Like, how do we write the slope? Well, recall our slope formula from pre-calc. M is equal to the change in y over the change in x. Well, in this case, you can see that since this f of a and f of x are our y components, we can write this as the f of x minus f of a. So this is the secant line between q and p. X minus a. We can write it like that. This is the slope of the secant line. We're going to call this... Oh, there's something wrong with my pen. Hold on. We're going to call this MPQ. We're going to call this MPQ. This is the slope of our secant line. Now, I'm just going to erase this. You can always pause the video, look back. So we know these are our points. Now, let's let Q approach P along the curve C by letting X get closer and closer and closer to A. So let's consider this X, and we're at point P. Let's consider this A. Let's let X approach A. So let's move a little bit. So look at this black arrow, and we're going to move to this green point right here. Now, let's draw a secant line. It's drawn here in green from P to our new point Q. We can call this Q1, let's say. Q's moved over a bit, so we'll call this Q1. Okay. Let's move a little closer now. Let's let X get even closer to A. And I think it's kind of hard to see, but let's move it along this black arrow right there, this blue point. That's where Q is now. We're going to call this Q2. Now, drawing the secant line from P, between P and Q2, you observe that, as I've written here, the actual red line is the tangent line at P. You can see that the secant line from P to Q2 has almost the same slope as the tangent line at P. Observing Q1 and Q, the secant lines there, you can see that as I move closer, as X gets closer to A, as Q gets closer to P, the tangent line looks more and more and more, not the tangent line, the secant line looks more and more and more like the tangent line at P. So by letting Q approach P, it turns out that MPQ, the slope of the secant line between P and Q, ends up approaching the slope of the tangent line at P itself. Oh, I don't know what's wrong with my pen here. The slope of the tangent line at P itself. So, turns out that MPQ, as Q approaches P, because X is approaching A, turns out that MPQ is approaching M, and M will be the slope of the tangent line at P, which I've drawn in red here. So basically, in summary, as Q gets closer to P, the slope of the secant line gets closer to the slope of the actual tangent line at P. So as we get closer and closer and closer and closer and closer, our secant line slope will basically end up being the slope at the tangent line, at the point P of the tangent line. So how do we write this then? And how do we write this as an expression? Well, we can write this as an expression. We can write this as a limit, as I said before. The derivative is just a special type of limit. Now, what does this limit look like? Now, our slope m of the tangent line, we're going to say the limit as x approaches a, so as x gets closer to a, of f of x minus f of a over x minus a. So as x gets closer to a, the limit of this will give us the slope of the tangent line at the point, well, a. And, well, in this case, at the point P, but as x approaches a, we'll get the slope of the tangent line there. So we'll get the actual slope. This is basically giving us our derivative. This is one of the limit expressions of the derivative. So, well, how do we use this expression? Well, let's do an example. I'm going to do that on the next slide. Okay, example 1. Find the equation of the tangent line to the function y equals x squared at the point 3, 3, 9. So, what do we do? Well, let's write down that equation that we found. Well, the slope at a point on a function is equal to the limit as x approaches a of f of x minus f of a all over x minus a. So I want you to look at this closely. So what is our f of x? What's f of x? Well, f of x, by looking at the question, we see that f of x is just x squared. F of x is just x squared, but what's f of a? Well, we're given a point, 3, 9, as you can see. So f of a, our a is 3. So if f of x is equal to x squared, f of a, which a is 3, just plugging 3 into the equation, and we end up getting 9. Okay, so how do we put this all together now? Let's write it out. M is equal to the limit as x approaches a, and a is 3. Oh, a is 3. F of x, so what's f of x? Is x squared. What's f of a? It's 9. Well, so x squared minus 9, because there's a minus sign right here, divided by, so we got x, it's just x, and what's a? A is 3. Now we just solve the limit. So how do you solve the limit? And well, in this case, x approaches 3. You just factor the top, and we get x plus 3, x minus 3, and we get x minus 3. These cancel. So we end up getting the limit as x approaches 3 of x plus 3. And what is that? Just plugging in 3, that's 6. So what did we just find? Well, we just found the slope of the tangent line at the point 3, 9. So let's take this a step further. Let's take it a step further. So what's the equation of this tangent line? So we have the slope, but what's the equation? Well, recall, the equation of a line from pre-calc is mx plus b. Now, you should be no stranger to this. So let's find the equation. So we have the point 39, and we have the slope. So if you put this together, so first we got the slope, we got 6x plus b, because the slope is 6. And we have the point, so now we're just gonna plug the point in. I'm gonna say 9, because 9 is our y, is 6 times 3, and plus b. And we solve, and we get b is equal to -9. Oh, for some reason it won't let me write there. Is equal to, I'll just erase this. I'll erase something. Solve this up here. We get b is equal to -9. Go over there, and we'll say our equation of our tangent line then is y equals 6x minus 9. This is the equation of our tangent line. Okay. But I have to mention something. So this leads into our next topic that we're going to cover on the next slide, is that this expression, there are multiple ways we can express the derivative as a limit. So let's see how that happens. Okay, now let's consider that equation we just worked with. The limit as x approaches a of f of x minus f of a, x minus a. Okay, so let's say h, let's put this variable h in there. H is equal to x minus a. Okay, if h is equal to x minus a, then x is equal to a plus h. Okay, now let's plug these in. So where do we see an x minus a? We see x minus a right here. And where do we see just x? So well, we see x right here. So let's plug these in. M is equal to the limit f, and we're going to plug that expression in, a plus h minus f of a. Now, a is just a number. And we got h. But what's our limit? What's approaching what? What's our limit? Here we have x approaching a, but we just replaced x everywhere. There's no x in the equation, so what's approaching what? Well, for x to approach a, we see that, look at this expression closely. X minus a. X approaches a. The difference here is 0. This equals 0. This expression ends up equaling 0. So as x approaches a, h must approach 0. So our limit here is h approaches 0. Okay, so now we just got a second expression for our derivative. This is a second expression. Well, there's some more commonly used expression you'll see. Probably the most commonly used out of these expressions, and you'll be working with it the most. And I'll be working with it a lot in the tutorial video when I do some examples. So what is that? So recall I said that a is just a number. Now let's replace a with a variable. variable x. Okay, so let's do that. Let's replace all the a's in this equation with x's. So m is then the limit as h approaches 0 of f of x plus h minus f of x all over h. This is our third and probably the most commonly used expression for the derivative when it's written as a limit. So, okay, we got this expression. So how do we work with it? How do we use it? So let's go to the next page and let's do an example. Okay, so here's our example. Find the derivative of the function x squared using the definition of the derivative. So the limit definition of the derivative. So let's do question A. Let's find that derivative. So what expression did we just get at the end of the last slide? Well, m is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so what do we do? So let's look at the easy part. Well, what's f of x? Well, f of x in this case is obviously it's given to us in the equation is just x squared. Okay, but what about this f of x plus h? Now, this is where we need to be careful. F of x plus h. A lot of students, their initial thought is f of x plus h is x squared plus h. This is wrong. This is totally wrong. Very, 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 very wrong. F of x plus h is not x squared plus h. It's x plus h in brackets squared. There is a big difference here. And please do not make this mistake. And I'll tell you a story. When I was doing Calc 1, I used to think of this as having h to be the closest to x. It was just like this weird memory trick I had in my head. I recommend you understand why we're doing this, but this weird memory trick I had was that x needs to be like the first thing affecting h. You could think of it like that. It was just this weird trick I had in my head. If you find any use for it, I guess it works, but I'd rather you understand it too. But a quick check is that x is the closest to h, and so how do we go about this now? Now we got this f of x plus h, and we just found our what the expression is. Do not make this mistake. Do not do this. DND, do not do. So how do we put this all together? Well, let's write our limit expression out. M is equal to the limit as h approaches 0. So what's our f of x plus h? Well, it's x plus h squared. What's our f of x? Well, in this case, is now we got minus x squared is our f of x. And this is all over h. So I want you to pause the video, write everything you need down. So I'm going to do some erasing. So I'm just going to erase this part really quickly to make some room. So you got that down. And now we're going to return back up. I'm going to start from this up here. So I'm going to erase this too. So we got our expression. M is equal to limit as h approaches 0 of x plus h squared minus x squared all over h. So let's expand this. What do we get? is equal to the limit as h approaches 0 of x squared plus 2xh plus h squared. This isn't anything unfamiliar. Minus x squared. So that's our, our f of x there. All over h. So we got some cancellation here. These x squareds, they cancel each other out, and we're left with m is equal to the limit as h approaches 0 of 2xh plus h squared h all over h. So we got more cancellation, and we just end up with 2x. M, the slope of the tangent line, is equal to 2x. Well, what do you notice here? Well, the slope, as I said at the start of the video, the derivative we got here, which is 2x, is a function in itself right here. So if I plug in different inputs, I'll get different slopes at different points on the function. Because recall, x squared. Oh, can't I? It's so strange. For some reason I can't draw on one side. Okay. So there we go. Got my x squared function here. Well, if you look at this, actually I'll draw this a little better. That's so strange. Okay, so I got my x squared function here. Pretend this is the origin right here. Well, let's look at a point right here. Let's draw a tangent line to this point. Right there. Well, it shouldn't be almost looking vertical. Hold on. Let's pick this point right here, and let's draw a tangent line right there. This point right here. Now, well, we see this tangent line. Now, let's pick a point here. And let's draw the tangent line here. Well, the slope of the tangent line here is positive, while the slope of the tangent line here is negative. You can see that the slopes of the tangent lines are different at different points. Well, here it's like this. It's not this. These slopes, not all these tangent line slopes are equal. Sorry, it's a terrible drawing. So these tangent line slopes are not equal at different places. Not this slope is not the same as the slope at this point. And at the origin, the slope is 0. It's just a horizontal line. So we see that the slope changes depending on the point. So that takes us into the next part. Find the slope of the tangent line at the point 1, 1. Well, I'm going to do some erasing, so take this down. So let's go into part B. Well, we found our slope of our tangent line to be equal to 2x. And we want the slope of the tangent line at the point 1, 1. So how do we find that? Well, it's simple. We got x equals 1. We just plug that in. The slope of the tangent line at 1, 1 is just 2. That's the slope. That's our m. Now, I want to introduce something really quickly here, is that we found the derivative of y with respect to x. And we can write this m part, our slope, we can write this is equal to dy by dx. Dx. So the derivative of y with respect to x. And this can be in turn written in short, because, this is kind of a tedious thing to keep, writing over and over. This can be written as just y with an apostrophe, and we call this y prime. Y prime. That's how we say it. Okay, so let's go on to, this is our part B. Let's go into our part C. So remember, What is the equation of a line? Well, it's y equals mx plus b. What's our m here? Well, let's plug that in. We got 2x plus b, and we got a point, 1, 1. So let's plug that in. We got 1 is equal to 2 times 1 plus b, and our b is equal to -1. So what is the equation of our tangent line? Well, the equation of our tangent line is just 2x minus 1. Ta-da, we're done. We answered all the questions. So we seen these notations. I'm going to go back to this really quickly. We'll be seeing these more often in our next videos, and you'll be seeing it more often in your classes, in Calc 1. So keep that in mind. My next video, I'll be doing more questions using the limit definition of the derivative to help you guys, get a better hang of it. And I'll also be doing a short summary video of everything we've done in this video in case, you don't have much time. So math on the go, basically. And I'll be doing a short summary of what we've done here. Probably won't do any example questions. It'll just be, here's the equation. What is the derivative really quickly. So thanks for watching. Tune in for the next video.